Okay, so I want to talk about C a little bit because we sort of got into it a little bit in the last equation and the last video. So I want to give a slightly different take on it. And so let's come up with a, let's say dx dt. Let's call that t over x squared. So we're just looking at a differential equation that's a little bit more complicated than what you've seen or what will be in the book, but that's okay, you can handle it. So just like we said, the first thing we're going to do is we're going to get all the x's on one side and all the t's on the other side. So we're going to get x squared dt is the x squared dx is equal to t dt. Okay, so then what we're going to do is we're going to take the integral of both sides, because anything we do to one side we can do to the other side. So we're going to get 1/3 x cubed plus c equals 1/2 t squared plus c. Okay, and we've got two c's, c1, c2, and so I'm going to write 1/3 x cubed equals 1/2 t squared plus c2 minus c1, and I'm just going to rewrite that as 1/3 x cubed equals 1/2 t squared plus c. Well, because as I said in my previous video, C2 is an unknown constant, C1 is an unknown constant, so if I subtract them, I'm left with an unknown constant. I don't need two unknown constants, I can just have one unknown constant. Okay, so then the next thing that I'm going to do is I'm going to multiply both sides by 3. So I'm going to get x cubed is equal to 3/2 t squared plus 3c. But then I'm going to write that as x cubed is equal to 3/2 t squared plus c. And you go, wait a second, where'd the 3 go? Well, remember, once again, c is a known constant. When I multiply c by 3, I get an unknown constant. So if c is an unknown constant, then 3 times c is also an unknown constant, so I might just write c. So then you go, okay, so now I'm going to take the cube root of that. Say x equals the cube root of 3/2 squared plus c, right? No. Bring you a curveball. Because taking the cube root, I'm not just taking the cube root across the board. I have to take the cube root of everything on the side. And I have to take the cube root of everything on the right side. And in this case, it matters. It gets locked under that cube root symbol. So if I say then is to be equal to the cube root of 3/2 t squared plus c. Okay, and this relates to the Pythagorean. This specific example doesn't relate to Pythagorean theorem, but suppose I've got x squared is equal to plus 16. Well, that's simple enough. That means that x is equal to plus minus 5. Well, if I take the root of everything, so if I got x squared equals 3 squared plus 4 squared, Well, then why can't I just take the square root, take the square root, take this that, and get x equals 3 plus 4? But it doesn't work that way. It doesn't work that way. Because if x squared equals 3 squared plus 4 squared equals plus or minus 5, it does not equal 7. Does not equal 7. If I've got x squared equal to t squared plus c, I have to do, let me go back. X is going to be equal to the square root of 9, or it's going to be root squared plus 4 squared, all under the square root. So if I say squared plus c, then x is minus the square root of t squared plus, and it gets locked under the square root. Just using a little thing up here. Let's do another one. If I say of e to the x dx equals the integral t, well then I get e plus c equals 1 squared plus c. So I can say e to the x equals to 1/2 t squared plus c. If I'm going to solve that for x, I'm going to say that ln of e to the x is equal to the ln parentheses 1/2 t squared plus c. So x equals ln of 1 t squared plus c. Yeah, when I do that inverse of things like square root, that c gets locked in the parentheses. So that's why